SwayamPrabha. Digital India. Educated India.
Good morning everybody. Today we will discuss about large eddy simulation of turbulent flows. Now, why do we go for large eddy simulation? We know the exact equations that are full Navier-Stokes equations in 3 dimensions and continuity equation. These are available, and if we have numerical solution technique known and very accurate discretization procedure is available, then in principle we will be able to solve these equations with very high level of accuracy in the flow field. Now, problem is at high Reynolds number, situation becomes different. For high Reynolds numbers, the flow field usually consists of several eddies or several eddy structures. And this is one typical example, that if we use a basically probe and we measure, for example, velocity component u at 1, 2, 3, 4, 5, 6 points over time, we will see the signals that we get are having different wave numbers and different amplitudes at different locations. Now, this signifies that we get multiple frequencies in a flow field. Yet another small observation which we would like to explain. Let us take a very simple wet flow where the top plate is moving with the velocity u0. Gap between two plates is given by L, and this gap is divided by 100 points, and the flow field, let us say it is 3-dimensional flow field. Now we will see that the grid Peclet number, which is given by delta U into delta N, delta U into delta L by nu, that for stable calculation has to be less than equal to 2. So now delta U means incremental velocity. Here from 0 to u0, delta U we can write u0 by n if n is number of grid points in the cross normal direction, and delta L is given by L divided by n into 1 by nu. So we can get here u naught into L by nu, which is the Reynolds number, is less than equal to 2n squared. N is 100 we have taken. So, basically in one direction we have taken 100 grids, means the other directions, y and z directions, also 100 points. So 100 by 100 by 100 is the grid mesh, size of the grid mesh in the domain, 100 by 100 by 100. In some such situation, the limitation that comes on Reynolds number is basically 20,000. So in a flow field where Reynolds number is 20,000 can be resolved by using 100 by 100 by 100 grids. So we can see that grid size and Reynolds number are related. Large eddy simulation is a technique intermediate between the direct simulation of turbulent flows and the solution of Reynolds average Navier-Stokes equations, or RANS. We have already discussed RANS solutions. In large eddy simulation, the contribution of large energy carrying structures to momentum and energy is computed exactly, and only the effect of the smallest scales of turbulence is modeled. Since the small scales tend to be more homogeneous and universal and less affected by the boundary conditions than the large ones, there is hope that their models can be simpler and require fewer adjustments when applied to different flows than similar models of RANS equations. So, basic idea is that when we do not apply any model, we solve directly the equations in a given domain. Our grid size should be such, grid mesh should be such that the smallest scale of turbulence, which is known as Kolmogorov scale, that smallest scale of turbulence should be captured. And as we know that scale smaller than Kolmogorov scale, usual dissipation takes place and they destroy themselves. So the Kolmogorov length scale is given by eta. We have written nu cube by epsilon. Nu is the kinematic viscosity and epsilon is the dissipation rate of turbulent kinetic energy. This whole to the power 1 by 4. And commensurate with Kolmogorov length scale is a time scale, which is nu by epsilon to the power half, and velocity scale, which is nu into epsilon to the power 1/4. So in a flow field, if we can have grids or grid mesh in such a way that the smallest size of the length scale, that means Kolmogorov scale, is captured and there is no dissipation error, there is no diffusion error in the numerical scheme, then representing exactly the turbulent flow of interest in a geometry is possible. So, in practice, we will see that in a given geometry, we will need 10 power 14, 10 power 15 grids, or even higher number of grids. Obviously, we do not have that computing power available all the time everywhere. Now, LES approach addresses this problem to some extent. What we do, we use filtered or average Navier-Stokes equations. So we apply filter on the Navier-Stokes equations, and this filter is synonymous to grid size. This leads to unfiltered scales, also called unresolved scales. This also leads to average scales or filtered scales, also called resolved scales, and then models can be applied to account for the dynamic effect of the unresolved scale. Typically, this is the spectrum and this is energy versus wave number. For smaller wave number, that means the large scale eddies, these are energy containing eddies, and for higher wave number, that means small scale eddies, high frequency eddies, turbulence usually decays, and finally we end up with a situation where the decaying turbulence, or this is called inertial subrange of turbulence. So if we want to capture the entire spectrum, we have to use grids which are, you can see the grid size is given by twice pi by k eta, and this k is wave number. So high wave number, that means the basically small scale, or the smallest, we have to go up to the smallest scale of eddies, that means very high frequency or very high wave number, which will correspond to a grid size, the smallest grid size. So at sufficiently high Reynolds numbers, the statistics of the motions of scale L is in the range L between LE, which are energy containing scales or energy containing eddies, and eta. Eta is L is between Le and eta. So we want to be somewhere here. So it is between, it is greater than Le and less than eta, somewhere here. So basically, universal form that is uniquely determined by dissipation independent of nu. From the second hypothesis of Kolmogorov, the spectrum is given by energy spectrum is, this is the absolute magnitude, k by k eta, epsilon to the power 2/3 and k to the power minus 5 by 3. On wave number plane, k lies between ke and kd, or ke and we can say k eta. We have written kd, let us read this as k eta, where ke is twice pi by Le and k eta is twice pi by eta. We have drawn also here, twice pi by eta is k eta, and again eta is Kolmogorov scale given by nu cube by epsilon to the power 1/4. So if we want to capture everything, the full spectrum, then we have to have presence of wave number k eta, and that is the, as we said, that the high wave number, that means small scale eddies, and high wave number means twice pi by eta, where eta is the smallest scale. So DNS grid, if we want to perform DNS, grid size will be equivalent to eta, which is given by twice pi by k eta. K eta is basically high wave number, high frequency, and small scale, smallest scale of eddies, and that small scale is given by eta. So this is the DNS grid size. As compared to that, LES grid can be much larger. Although LES also requires very fine grid as compared to usual RANS computations, but LES grid can be much larger than the DNS grid. Maybe on wave number plane, the grid size will come in the inertial subrange, which is on the, where the slope is minus 5 by 3, k power minus 5 by 3 of energy, and the scale is, that means grid is smaller than energy containing scale, but it is larger than energy containing scales, but smaller than smallest scale, or smaller than the high wave number. So the scales that correspond to high wave number is small, highest wave number is the smallest. So we can have grids larger than that, but smaller than energy containing eddies. So this is the energy spectrum, and this is the dissipation. and this is non-dimensional wave number, this is non-dimensional energy, this is non-dimensional dissipation. So these are energy containing eddies, and this is inertial subrange, and we can truncate somewhere at the end of inertial subrange in such a way that grid corresponds to that particular wave number. So that means if we truncate here, grid will correspond to, basically, say if we say L, so corresponding wave number will be twice pi by L, and that twice pi by L is smaller than twice pi by eta, because eta is the smallest, but that twice pi by L will be larger than twice pi by Ke, because Ke is energy containing larger eddies. So, and this is the dissipation we can see. Now when we truncate the filter or the grid in this way, we have to account for this dissipation. If this is the actual dissipation, our model, we are truncating grid somewhere here, so we have to account for this dissipation, because we are not going up to the smallest scales of eddies or the highest wave number. So this is to be modeled. Now assume that we are using the filter which is at the end of inertial subrange, fine enough, but smaller than Kolmogorov length scale. So this is the averaged continuity equation, filtered continuity equation. This is the filtered Navier-Stokes equations. It looks like Rand's equations, you can see, but here this bar means filtered quantity. So del u I bar del t del xj u I bar u j bar equal to minus del p del xi plus 1 by re del 2 del ui bar del xj minus del xj tau ij. And what is tau ij? Tau ij, if we apply filter operation on the basic Navier-Stokes equations, we will see, we will produce a term which is given by tau ij, and this is uy uj over bar, this over bar is filtered, minus u I bar u j bar. So this tau ij is called subgrid scale Reynolds stress tensor, and this requires to be modeled. Here you can see this part, if you exclude del xj of tau ij, is a kind of exact Navier-Stokes equations in full form. Only difference is each quantity is filtered quantity, and whatever is unfiltered, that means tau ij, when you apply in original Navier-Stokes equation del xj, ui into uj is the term, and you apply filter operation on that. Then if you perform the algebra, we will see when we write del x of u I bar uj bar, we actually transfer this quantity ui uj over bar minus ui bar uj bar to right hand side. This has some similarity with Reynolds stress, but it is not Reynolds stress. These are not fluctuating quantities. These are spatially unfiltered quantity which are not yet resolved, and we write them on the right hand side, and we say that we will be modeling it. So let us first discuss standard subgrid scale model. The standard subgrid scale model is briefly described here, referred to as Smagorinsky model. If the filter discussed earlier is applied to Navier-Stokes equations, subgrid stresses will assume the form I have already said, basically u I bar u j bar over bar minus u I bar into u j bar plus u I bar into us. This us is the unfiltered quantity over bar plus uis uj bar over bar plus uis ujs over bar. So where the over bar represents the filter operation. These stresses are similar to the classical Reynolds stress that result from the time average or ensemble averaging of the advection fluxes, but differ that they are the consequence of spatial averaging, and they go to zero if the filter width goes to zero. The most commonly used subgrid scale models are based on gradient transport hypothesis, which correlates tau ij to the large scale strain rate tensor, which is given by tau ij equal to minus twice nu t, something like eddy viscosity, Sij bar plus Kronecker delta Ij, because we know that this will be added with the normal stress tau kk by 3. Otherwise, this will contribute as shear stress. So nu t is given by Cs delta square into twice Sij over bar Sij over bar into s to the power half, Sij into Sij, Sij bar into Sij bar to the power half. Whereas mod S is given by twice Sij bar to the power half. So basically this can be written as mod of S. S is in principle strain rate tensor, but the variables are filtered quantities. Sij bar is half u I bar del u I bar del xj plus del xi uj bar. These are all filtered quantities. From there we get Sij. And Sij into Sij to the power half is basically the mod value multiplied by 2, of course, that is mod S. So nu T is basically given by Cs delta square into mod S. That is nu T, and then that is multiplied by the strain rate tensor, which is given by this. Now, dynamic modeling of the subgrid scale stresses were introduced. So this is then, I'll go back. This is then very simple. If Cs is known, nu T will be known. If nu T will be known, then we can calculate from the field variables Sij, tau ij will be known, and if we can feed in tau ij here, we'll be able to solve the full Navier-Stokes equations. That was the idea of original Smagorinsky model, which was modified by Germano. Dynamic modeling of the subgrid scale stresses were introduced by Germano in 1991. The dynamic model of Germano is based on the introduction of two filters. In addition to the grid filter, which we have already identified by an overbar, in addition to the grid filter, which define the result and the subgrid scale, and it is denoted by overbar. In addition to that, we introduce a test filter, and how the test filter behaves we'll describe later. So this is basically a grid filter. So tau ij minus Kronecker delta by 3 tau kk, we have seen original Smagorinsky model. It is minus twice c. This c, uppercase C, means Cs into delta squared, or Cs squared. Delta will take out. So this C is Cs, C subscript S squared. So C, then delta bar squared, that means average grid size, modulus of S bar into Sij overbar. And we can write this identity as minus 2 C into beta ij. Remaining terms can be written as beta ij. The quantity C is the Smagorinsky coefficient. Basically, this is square of the original quantity. Germano et al. In 1991 and Lilly suggested a method to calculate C for each time step and grid point dynamically from the flow field data. The width of the test filter is larger than the grid filter. We are using a test filter. This is the size of this test filter is larger than the grid filter. The test level subgrid scale stresses or subtest scale stresses Tij can be given in the similar way we can write Tij is Ui Uj over bar with a circumflex, Ui bar circumflex, Uj bar circumflex. The bar and circumflex together, this is basically averaging over the test filter size. Our test filter is having a dimension larger than the grid filter. Now, equation 40 can also be expressed in terms of Smagorinsky's closure. So, just the way we wrote the closure model here, so Tij can be casted in the similar way. We can write Tij minus Kronecker delta by 3 Tkk equal to minus 2 C delta circumflex square into mod of S bar circumflex and Sij bar circumflex. And this entire identity can be written as minus 2C, and this can be clubbed together as alpha ij, where Sij with circumflex means again the like strain rate tensor, but these velocities are not average on grid filter, but these velocities are average velocities on the test filters. So del xj ui circumflex plus del xi uj circumflex, and this filter size is basically delta 1, delta 2, delta 3, all are with circumflex, that means with higher dimension. It is bigger than delta 1, bigger than delta 2, bigger than delta 3 to the power 1/3. Now it is done in such a way that delta test filter level by delta grid filter level equal to 2. So we can, that means in all the directions, x, y and z directions, it is basically double. Now on xy plane, if it is double, then this may be the grid filter and then this will be the test filter. So if we have three-dimensional, mostly, I mean always it is alias, mostly it is three-dimensional. So you just imagine this repetition of this in the third dimension. So that means that a grid with this much length on x and y direction and same length in z direction, imagine the cube, and imagine the cube with, again, with this much length, this much height and this much depth. So ratio of test filter by grid filter will be 2. So this is a coarse grid volume, this is the fine grid volume, and we are representing them in two-dimensional plane. Extension in 3 dimension is straightforward, you can well imagine, and it will be done in such a way that grid filter, which is delta grid filter, is basically, smaller than the test filter, and test filter and grid filter, their ratio is 2. This is double in all the directions, x, y and z. the major contribution to the subgrid scale model brought about by Germano, I have already mentioned about it, is but here emphatically the contribution which is highlighted is the identification of the consistency between equation 39 and 40. That means consistency between this equation, which is test level subgrid stress or sub-test scale stresses, test level subgrid stress and the grid level subgrid stress, they are identical. That means we can establish a relationship between, again, this Tij and tau ij. How? If we write basically Lij, which is again a tensor identity of stress tensor, is Tij minus tau ij, and this is averaged over the test level. So then it is twice C alpha ij, which is already test level, plus twice C, because tau ij was at the grid level. Now we are applying filter with a circumflex. So beta ij is originally, this is the grid level representative of the grid size squared S bar mod into Sij. This Sij is again half del ui del xj plus del uj del xi. Ui and uj are grid level velocities, and alpha is again delta square, but this delta is added with a circumflex, that means test level grid representative, multiplied by modulus of S circumflex into Sij bar circumflex. This means again half del del xj of u plus del del xi of u, del half into del del xj of ui plus del del xi of uj. Ui and uj are average velocities at the test level, test filter level. So equation 41, that is this equation, then 43, that means this equation, 44, 45 and 46 are 5 independent equations which cannot be solved for the model constant C because it appears in a filter operation in equation 44. So what we get is minus twice alpha ij equal to Lij minus twice C alpha ij plus twice C beta ij with the circumflex. Now this averaging is because this is unknown. C is unknown to be determined. So this is a very, very difficult situation. Now many people, many researchers applied different thoughts to resolve this. Very successful solution or very successful recommendation came from Piomelli and Liu. They have suggested a simpler approach based on modification of equation 44 as twice C alpha ij equal to Lij minus C star beta ij, where C star is substitute C. The value of C star assumed to be known. In the event, minimization of the sum of the square results. So if C is known, then we can write, then we can break this tie, we can write expression for this C with Lij and beta ij as minus half Lij minus C star beta ij circumflex divided by alpha mn into alpha ij, where Lij is ui into uj averaged over test filter minus ui into uj, both are at test filter level. So this is the equation for calculating model coefficient C. There are various ways to obtain C at step n. So this, if like Piomelli and Liu, they assume that C star is known. If C star is known, then this can be resolved in this way. And how instead of C we can write C star? There are several justifications. Piomelli and Liu indicates that there is no significant difference between 0th and first order approximation for estimating C star. The 0th order approximation through the value at the previous time step. So whatever was calculated at the previous time step, that means Cn minus 1, if n is the ongoing level of calculation, can be called C star. Even though the local averaging procedure will come to that later. So Piomelli and Liu recommended that previous label C value in each cell, that means at n minus 1th level C value at each cell can be considered as C star, and then that can be substituted here, and then 48 can be perfectly evaluated and C at nth level will be known. So that is what is the recommendation of Piomelli and Liu. Even though the local averaging procedure, even after that, there may be some problems. Some problems means there may be some negative C values. And that is why, a negative C value will not be able to close the equations properly. There will be numerical instability. So even though the local averaging procedure of Zhang et al. Is invoked, spurious value of C appeared during the calculations. So now, having found out C in this way, Zhang recommended finding out some formulae for finding out local average. And even after local averaging, if there is any negative C value, that can be restricted by putting or applying this limiter, which was very scientifically done by Ghoshal et al. Ghoshal, Axelwall, Moyne, it was a famous JFM paper. But, we can adapt that whatever is the value of C after this, closure of subgrid test level grid and the usual grid, that C can be averaged from each cell from its neighbors, and even then if there is some negative C value, we can apply this limiter that negative values, if it is 0 or above, it comes as such, but if there is any negative value, then negative value will be converted into 0. So, and then in each cell we get the value of C, and these C's are different in each cells. That is the beauty of LES, that it doesn't assume the same scales throughout the flow field. So I have given a flow chart so that when you calculate it, you can apply the algorithm very properly from divergence free velocity field, which are all U bar, V bar, W bar. We apply again boundary conditions on U bar, V bar, W bar. Calculate test level velocities. Now test filter, as I said, is double the size of the grid filter, but these values are not computed. They are basically evaluated through a very powerful interpolation scheme, and this method was very effectively described by Najar and Tufte in 1996. How to create test level values, test filter level values from the grid filter values. Then calculate Lij, which is again Ui into Uj averaged over test level minus Ui test level Uj into Uj test level out of U bar, V bar, W bar and U averaged over test level, V averaged over test level, W averaged over test level. You calculate Lij, and as we can see, this quantity is the average over U I bar, U j bar. From these values, these test level values are created. Now calculate alpha ij, which is test level grid size into S mod at test level, Sij at test level. Then calculate beta ij, which is again grid at the the grid size, representative grid size at the grid level, delta bar squared S bar mod into Sij bar. Sij bar means half del xj ui bar plus del xi into uj bar. So basically strain rate using the grid level velocities, grid filter level, grid filtered velocities out of u bar, v bar, w bar using grid filtered quantities. Calculate C star into Bij, beta ij, C star into beta ij over circumflex out of C star, and C star equal to old C and beta ij with suitable averaging technique. From here, calculate the value of C, Cxyz equal to minus half Lij minus twice C star beta ij. This is averaged over filter size, test filter size, alpha ij divided by alpha mn. These alphas are, as you can see, these alphas are all at the evaluated at the, using test level filters. Now we go for local averaging of C out of neighboring C and get the final C, and after having obtained final C, if any value in any cell value of C becomes negative, we have to apply the limiter C greater than equal to 0. Now we have come across the wall function treatment to apply the boundary condition at the wall. Now in the case of LES, laminar profile may be used if Y plus, since the grid size is very small, the grid has to resolve in such a way that near the grid, near wall grid point, Y plus should be less than 1. Then also we can apply basically log law. So this is u bar plus equal to 1 by kappa von Karman constant log y plus beta. And there is another prescription of Schumann. This is Schumann is very well known LES contributor from University of Munich. So this is calculating the wall shear stress, then the current level of filtered value. From there calculate the tau xy through this averaging, and you can see that this bracket means the time average quantity that is averaged over a plane parallel to the solid wall. So applying boundary conditions is slightly involved. One has to see that, but it is simple if the grid size is kept below 1. Now I will show some results which are really to be mentioned. This is result of a model or simulation for jet flows, and as you know, for turbulent jets, getting a self-similar profile is the acid test. And what is a self-similar profile? You have to plot the velocity profile at any height, that means at any distance from the nozzle, or if it's impinging jet, at any height from the plate on which the jet is impinging. Plot any height from the plate or any level from the nozzle, any depth from the nozzle. If we plot W by W max, that means local velocity from the nozzle center line, by the center line velocity W max at a given jet, and the other axis will be distance from the center line by BW, this is called half jet width. That means where the distance where the W max is exactly half. So this half jet width, x by half jet width versus W by W max, and here for we calculated for Reynolds number, you can see 10,000, and different jet heights, z equal to 12. Z is a direction perpendicular to the plate. 12, 10, 8, 6, 4, and these are different symbols. You can see all the lines are collapsed on a single curve, and this is a very carefully done experiment by one group, Namar and Otugen, and this is the result. So this result which I showed was published in International Journal of Heat and Fluid Flow, and this was large eddy simulation of flow and heat transfer in an impinging slot jet. Another study was done for impinging jet on moving surface, and yet another study was done on large eddy simulation of high Reynolds number turbulent flow past a square 3D square cylinder. Now in the second investigation, we found out this is on a slot jet. Again, it is slot jet is being used for cooling a heated plate, and these are basically the dotted lines are earliest calculation based Nusselt number plot, but Nusselt number, this is span wise average Nusselt number, and one side from the slot jet center line. Those have been plotted and have been compared with very carefully done experiment of Professor Schlunder and his group in the University of Karlsruhe. Then for different Reynolds number and different plate velocities, this is moving plate I mentioned about, what are the Nusselt number distributions we obtained, and some were compared with the experiments too. This is a study where we compared basically the time averaged lift coefficient, drag coefficient, RMS lift coefficient, RMS drag coefficient, Strohal number, reattachment length for flow past a square cylinder, alias computation. You can see present computation means this paper which I referred earlier. Lead author is Y. Srinivas, and there we compared with different experiments conducted by different groups across the world. This is Lin and Rudi, this is Wang and Vanka, this is Nada and Nakayama, so Durau in Portugal, Norberg in Sweden. So we and all these quantities were compared. We do not have time to go into detail of this comparison, but result of the results of this comparison were very satisfactory. I'll show you another striking feature, that these are basically streamwise normal stresses. Normal stress means U prime square bar, right? This is basically velocity. These are second moments, these are called, not directly velocity quantities. These are even more difficult to match. These are basically Reynolds stress quantities. The streamwise normal stresses close to zero at the central line and exhibits a peak on each side. So this is behind the square cylinder, and y is its x is different location. This is just behind the square cylinder. X is 0. A further distance away, x is 1, x equal to 1.5, x equal to 5.0, and y distribution. That means the basically distribution, this is depth average distribution in the cross normal direction of the normal stress. And then we compared it with the very carefully done experiments of Lin and Rodi and very carefully done LES study of Wang and Vanka. So you can see this dotted lines are Wang and Vanka's line. Our computation is the solid line, and these symbols are basically experiments of Lin and Rodi. We get a very favorable comparison. Now I'll just mention about that LES is very active field of research. Many groups are working across the world, and several exciting developments are coming. So this dynamics Magorensky model, which I explained today, is definitely good, and in very complex flows it works very well. There is yet another improvement by a group in France, that is called shear improved Magorensky model, SISM. The influence of the mean gradients is removed in such a way that mimics the energy budget for both isotropic and shear turbulence. If we get opportunity, we will explain what it means, and I have given the reference. This is a JFM paper by Levesque and his group. Incidentally, or fortunately, I would say that we could adapt this shear improved Magorensky model, SISM. Dr. Pankaj Saha, during his PhD, he very effectively adapted this model and applied on several complex flows with very exciting outcome. Thank you for your sustained interest.